Well, hello, everyone. This is Mike Stenstrom, and we're presenting the seminar today in the 200 class. And the title of the seminar is Removal and Recovery of Nutrients from Wastewater Using Side Stream Treatment Technologies. And I'm going to start the seminar out, and we have two guest speakers, Dr. Henryk Melcer, who is spent most of his career at Brown and Caldwell as a process design engineer. And those of you that have taken classes from me have benefited from my collaborations with him over the years on oxygen transfer and various and sundry things. And he has a PhD from the University in Glasgow. And then John Lee, I'm sorry?
Birmingham.
Birmingham, oh boy, what a terrible mistake. And then John Lee, Zhongtian, is one of our own. He's our alumni from 4 or 5 years ago. And he finished up his PhD with me and worked on the activated sludge process and looked at particle size for different sort of treatment options. And he's been working with Centrosys Corporation since his graduation. And so today's topic is related to things that all three of us have worked on over the years. You see some pictures here. The one on the left is Henryk and I when we were in Berlin the last time. It was just happenstance that we were there together, so we had lunch. And then on the right is John and Grace at their civil ceremony in the Beverly Hills Courthouse, which was a lot of fun. I attended that. I got to see the pictures of all the movie stars that had gotten married in the Beverly Hills Courthouse. So it's an interesting place to visit if you can. So this is the outline of what we're going to talk about. Opportunities for side stream treatment, benefits and challenges. And
Mike,
I mentioned...
Mike, can I interrupt there?
Yes, please.
My screen shows a recording notification, which is obliterating some of the slide.
There should be an X you can click on.
Oh, okay. Am I supposed to do that? I thought maybe it was at your end.
No,
Okay.
no, each person has to do that.
Okay.
Okay, so there's a lot of interest now on nutrient removal because we think Santa Monica Bay may be experiencing red tides from excess nitrogen. And the inland plants started to practice nutrient removal some years ago, nitrogen removal, but it wasn't really for eutrophication control. It was for reclamation and avoiding nitrogen in reclaimed water supplies. And so we're going to talk about these side stream processes because it's an attempt to perhaps remove 10 to 20% of these nutrients, but you don't have to rebuild the treatment plant. So it's a more economical way of doing it. And we're not talking about footprint specifically, but these processes have small footprint compared to some other options for nutrient removal. So we're going to briefly touch on nitrogen. It's a little simpler and more well developed. We'll talk about ways for removing phosphorus and describe some case studies and some pilot plants that are going on. And then we'll summarize. So this is the treatment plant schematic, and many of you have seen this in my class. It follows the traditional scheme of treatment plants in the United States. Now in this, I'm not showing the return streams from biosolids disposal. So what we have is these recycle streams that come about from the anaerobic digester. The supernatant can have almost 1,000 milligrams per liter of ammonia. And the dewatering process will deliver additional return flows also at high ammonia concentrations and at high phosphorus concentrations. And these typically go back to the head of the plant. And when you do that, it makes the whole nutrient removal process more difficult for the rest of the plant. And so we're talking about 20 to 30% of the nitrogen and phosphorus that could be removed if we can treat these streams. And so it's less than the total removal, but it's a step in the right direction. Additionally, if you do want to go to mainstream removal, doing this side stream makes the mainstream removal so much easier and less expensive. So we want to prevent nutrient recycle. We'd like to recover the nutrients rather than just throwing them away. And so this side stream treatment offers 20 to 30%. And the nitrogen and phosphorus use different techniques for this side stream removal, mostly. I'm going to talk about the nitrogen removal. It's accomplished in most treatment plants using autotrophic aerobic nitrification, followed by heterotrophic denitrification. It can be made to work well at SRTs in the 10-day range and at temperatures greater than 10 degrees C. And when the main plant is operating in the nitrification mode, it is easy to add a side stream treatment to enhance that. And so one of the challenges is having sufficient, readily degradable organic carbon to form this electron donor. And it's desirable to use the influence COD for this if it's sufficient. Often it's not sufficient. And sometimes we try to affect fermentation in the process to make some readily degradable organic carbon. And the side stream removal makes the nitrogen removal in the main process reliable and less expensive. So we know how to nitrify and denitrify in treatment plants. Plants like the Tillman plant and the inland plants for LA County have been practicing some version of these processes for getting on to 15 years now. Ledzik-Ettinger is the most common, or when we modify it with a recycle pump. And we get down to 7 milligrams of total nitrogen, approximately. That's nitrite, nitrate, and ammonia, total inorganic nitrogen. And if this 7 milligrams per liter isn't sufficient, we can design a Bardinfo to get down to 3 milligrams per liter or less. And options are available, such as modifications such as stepanoxic. And I cover some of this in my class, but stepanoxic is easy because you don't need a recycle pump. But none of these recover the nitrogen. They're going to convert it to nitrogen gas, which accomplishes at least half of our mission. We're going to try to do this at least cost. Preventing ammonia recycle streams makes it easier to remove nitrogen in the main process. And the various methods of precipitating phosphorus may remove some nitrogen, but it's not enough to prevent all nitrogen recycle. So this is one example of side stream treatment, and this is from one of my papers. And it's an example of reaeration in the recycle line. And so what you see there is a normal MLE type activated sludge process. I'm not showing all of the features, but you take the recycle and you run it through a separate reactor and you add the centrate that's high in the ammonia. And the reaeration reactor may have 12 to 24 hours retention time. It doesn't need to be very big because the flow QR is not very large compared to the main flow. So that's how we can maintain the small footprint. And so this process has actually been used full scale here around Los Angeles. I first observed it out at the Inland Empire treatment plant, Carbon Canyon, where it was working very well. And then it's been practiced at LA County at the Valencia plant. They have separate digesters, so they need something out there. Most of the inland plants don't have digesters. And so there's another process that's become popular, and it's Animox. And Animox is sort of newly discovered, newly being 30 years or so, which goes a sort of short circuit across the nitrogen cycle. And you can combine nitrogen in the form of ammonia and nitrite in sort of anaerobic conditions to make nitrogen gas. And so it's not the easiest process to operate, although we're learning how to do it better and better. And the challenge of this process is to create nitrite, stopping the autotrophic nitrification at nitrite, which we typically do at elevated temperatures and DO concentration. And since we're talking about elevated temperatures, the digester supernatants are excellent candidates because they're already warm. We don't have to heat them. And so Animox has been a rich area for microbiologists to work. And there's about 10 different species that have been identified so far. And there's lots of molecular biology undergoing away at many universities. There are two patented processes for Animox process that use different techniques for enriching and maintaining the cells. So the DC water treatment plant uses a big Animox process, a Demon process, which works very successfully for them. And there are other full-scale plants now as well.
Okay, so I'm going to step into phosphorus, give you some background. Phosphorus is like nitrogen. It's a critical nutrient for virtually all forms of life. It's those of you who are well versed in biochemistry will see that it shows up all over the place because phosphate bonds are extremely energy rich. And how we see it today is primarily in detergents and in commercial fertilizers. We tend to, from our industry perspective, we'll see high concentrations of phosphorus occur in runoff from various facilities, leaking septic tanks. Probably the biggest mass discharges from sewage treatment plants and runoff from fields that have had fertilizer applied to them without sufficient controls over the runoff. Next slide, please. Oh, do I have to? Oh, okay.
No, I'm doing it.
Okay, so global phosphorus mass flows. Well, this is an attempt which has been made by many people. It's kind of a conglomeration of a bunch of data. If you do the math, the numbers don't add up, but there's a lot of scatter in the data. What this tries to do is tell you how we see phosphorus move through our society, starting off with phosphorus that's mined. Some of it's diverted into industrial uses, but we see a large chunk of it end up in the global food system, which you can see how it's being consumed. And ultimately, after we've consumed a portion of the food that's being created, we end up with a bunch of things that we have to get rid of, or at least treat. And so there's a box on the right-hand side of the slide, which tries to explain how, from an environmental engineering perspective, how we can manage this loss of phosphorus from the global system. And you'll see at the very bottom there, wastewater treatment systems is really only a small component of all of this massive phosphorus that's moving through our society today. Next slide, please. So the chemistry of phosphorus is actually pretty complicated, and some of it is not extremely well understood. This is a representation of our best understanding of the different forms of phosphorus. And really, not to take the thunder out of John's presentation, the focus is really going to be on the bottom left-hand corner on the soluble reactive phosphorus, which is what the talk is geared towards, high stream treatment technologies. But we do see all these other forms of phosphorus in wastewater treatment plants. The major objective here is to convert everything into a particular form so you can filter it out. And it's that portion which is in a soluble content or soluble form, which is what the technology is geared to convert into a particular form. Go ahead. So traditionally, the approach has been to precipitate it chemically, and these three metal salts have been used over the last 50 years or so with different degrees of success. The downside in terms of it being a green technology is, while it works very well, it'll reduce the residual phosphorus in the treated effluent to very, very low values. But the downside, or the two downsides, number one, as you can see, the precipitated metal phosphate salt manifests itself as a chemical sludge, and you have to deal with that. And just a rule of thumb about if you employ chemical precipitation in a wastewater treatment plant, you'll end up increasing the total amount of sludge you produce by about a third, which will be inert chemical sludge, and that becomes a major headache. The other downside is the fact that this precipitated form of phosphorus is non-bioavailable, so it can't really be used as a form of fertilizer. Next slide. There's some detail here, but the two takeaway points are, firstly, the pH controls of the degree of success of chemical precipitation. And clearly, if you look at the bottom of the curves here, the optimum point for precipitation, phosphorus using alum or ferric salts is somewhere between 4.5 to 5.5 or so, or 6. Typically, we don't operate our treatment plants or see our influence of this type of pH, so we're not really working at the most optimum value, but it'd be nice if we could. The other takeaway on the right-hand side, there's a plot there of alkalinity versus, in this case, the amount of alkalinity that you would need to raise to pH 11. The purpose of showing you this is when you add metal salts for chemical precipitation, you will consume a lot of alkalinity. And if your influent contains minimal alkalinity, you could end up pushing the pH down below where you want to be, and certainly into an environment which is not suitable for biological treatment downstream. Next slide, please. So there's a lot of information here, but what you want to focus on is that this is just a simple diagram of an activated sludge treatment facility. The influent passing through an anaerobic tank prior to aeration, clarification, and the recycle. And the importance of the grayed out tank is that this is a selector. It's an anaerobic selector, which induces the release of phosphorus. And the biochemistry detail is really related to the fact that the organisms, the bio-P bugs, are will release phosphorus because they need to access a source of energy, which is contained in energy-rich phosphorus bonds. And they need to store the organics that come into the plant. And that's the mechanism that they use. They want to grab hold of this and store it internally in their cells until they're ready, or they enter an environment in the aeration tank where they can utilize the form of carbon. And the mechanism they use is this release of phosphorus. Fortunately, they wake up when they get into the aeration tank and they realize that they've lost a source, that their ATP source of energy storage. And what happens then is that they will suck up all of the phosphorus that released in the anaerobic tank. They tend to overdo it. In other words, they'll take up more than what they released in the anaerobic tank, the net result being an effluent phosphorus concentration, which is much lower than what's in the effluent. We call that the enhanced biological phosphorus removal process. And we make use of this release and uptake mechanism of phosphorus, which is stimulated by the ATP conversion. Next slide. This is an interesting micro slide which illustrates on the left-hand side, these are micrographs of cells which contain just a normal amount of phosphorus, but then when they uptake the phosphorus that is released in the anaerobic tank, you'll see those black circles in there. That's indicative of the fact that they've got really efficient uptake of the phosphorus that's been released in the anaerobic tank. Next slide. And this is just a rough mass balance to indicate to you that of the 100% of P that comes in the door, you're looking to produce an effluent with a very low level of phosphorus, so that most of it ends up in the solid stream, and that then creates the headache because some of that is released during biosolids treatment and then forms the basis of what John is now going to talk about in terms of a side stream treatment technology. Go ahead, John.
Yep. Yeah, first of all, thanks Professor Stensham for the invitation for the seminar. Yeah, be glad to be here and share my experience with the phosphorus recovery. Yeah, looking at the rough diagram of the mass balance of phosphorus in the wastewater treatment process, 90% of the phosphorus loading end up in the biosolids stream, or so-called side stream. Conventionally, most of the biosolids are treated as a solid waste through several steps, including thickening, digestion, dewatering, sometimes with drying or incineration. Recently, people figured out that the phosphorus is actually accumulated in the biosolids and could be recovered from it as a valuable commodity. So just want to point out that most of the effort currently are focusing on the solid stream, and the solid stream functioning as kind of a gold mine for the phosphorus recovery in the water resources recovery facility. Next slide, please. Again, this is a familiar slide. So this shows the speciation of phosphorus in both the liquid phase and also the sludge phase. What I want to focus on is basically to have a general kind of impression that most of the engineering methods that to recover phosphorus is basically convert non-reactive phosphorus to a form of reactive phosphorus, preferably soluble reactive phosphorus, like the also P or PO4P. That is the only reliable soluble phosphorus speciation can be recovered by the currently available side stream technologies. Maybe in the future there are additional new technology that can recover phosphorus directly from the non-reactive phosphorus form. But nowadays, most of the currently available technology still focus on the reactive phosphorus. Next slide, please. To achieve the purpose of getting the phosphorus from the solid phase, there is a very key important pre-treatment called a releasing of phosphorus from the biomass. Basically, what an engineer try to do is to solubilize the phosphorus from non-reactive form to reactive form by using chemical, by using acid phase digestion, or through anaerobic digestion process. As you can see, the detailed information in this slide, that different steps have different requirements and the different requirement for chemical addition or the duration of the pre-treatment. All the three processes have been commercially applied in large or small treatment facilities, but most commonly, the release of the phosphorus is achieved by either acid phase digestion or anaerobic digestion. Adding acidic chemicals can be a very effective but costly approach, but it may be beneficial and make a lot of sense for certain industrial treatment processes. Next slide, please. In the last 10 years, the Water Research Foundation has spent quite some effort to discover what would be the general framework to recover phosphorus from the water resources recovery facilities or a typical wastewater treatment plant. In general, there will be 3 steps to effectively recover phosphorus from the biosolids in the WRRF. The first step is concentration. The second step is release and then recover. Actually, the current infrastructure at a modern wastewater treatment process has achieved at least certain level of concentration and a certain level of release in the solid treatment process. Because of that, a certain level of phosphorus has been released from the biomass, and that is not a good. That is actually a disadvantage for the side stream treatment process because the phosphorus released phosphorus, if not controlled well, will form precipitation on process equipment and on process piping, which can cause a huge damage on process equipment or significant maintenance effort on process pipes. So the recovery of the phosphorus not only make environmental sense, but also improves the maintenance and possibly reduce the operational cost of the side stream treatment process. Next slide, please. In the next few slides, I'm going to introduce the principle of commercially available phosphorus recovery technologies in 2 categories. And the first one is the magnesium-based recovery, which means we use the magnesium as the metal salts for the recovery. A secondary category is calcium recovery, which we use a certain form of calcium to recover phosphorus from the either from the liquid phase. There are advantages for both and disadvantages for both, so we can talk about that in more details in the next few slides. As you can see here, the magnesium-based recovery is largely based on the formation of the struvite or magnesium ammonia phosphate. This chemical is actually a crystal that will form under certain chemical conditions in both liquid and solid and sludge phase. The important chemical conditions including a high concentration of ammonia and a relative high concentration of phosphate in the stream. In addition to that, we need fairly good amount of magnesium to facilitate the nucleation, crystallization, and the granulation of the struvite in a certain type of reactor. Next slide, please. So this schematic shows the 2 approaches to use the magnesium-based recovery. The first one is to recover struvite, to form and recover struvite in the liquid phase. The liquid phase means either thickening supernatant or dewatering centrate or filtrate that contains high concentration of ammonia and the relative high concentration of phosphate. The specific numbers for ammonia concentration and the phosphate concentration are kind of trade secret for most of the commercially available technologies, because those are the key controlling parameters to make a good crystallization, but not create too much nucleation in the process. On the right-hand side, you can see we can also form struvite and recover the struvite directly from the digested sludge. The principle of the chemical reaction is identical as if in the liquid phase recovery, but the concentration of ammonia, the concentration of phosphate, and the concentration of magnesium will be different and will be optimized in a different controlling principle. So, but in generally speaking, recovered struvite is a proven technology that can be achieved through liquid phase recovery or sludge phase recovery. Next slide, please. And of course, because of the different kind of chemical reaction environment, the formation of the struvite will be quite different. On the left-hand side, the photo shows a granulized struvite that is formed through the liquid phase recovery. On the right-hand side, it is the struvite crystal that is directly recovered from the digested sludge through digested recovery technology. The chemical content of both products are very similar. The purity on the left photo shows is about 98%, and the purity of the struvite on the right-hand side photo is about 95%. So the quality of the struvite recovered from both processes are fairly comparable, but there are different factors will impact the recovery ratio. In generally speaking, the recovery ratio is higher in the liquid phase, and the recovery rate from the digested sludge is lower. So there are advantages and disadvantages for both processes. Next slide, please. Oh, there's a typo on the title. Sorry for that. So this slide will be the calcium-based recovery. What we are looking at is there are only limited calcium phosphate that is bioavailable. As Professor Melcer, Dr. Melcer introduced previously, the hydroxyapatite is also a form of calcium phosphate, but that is not biologically available. Brucite, as far as I know, is the only kind of calcium phosphate that is biologically available, and it's actually a fairly good fertilizer for certain plants, certain economical plants, including corn. So this is why we focused on the brucite recovery in a pilot test effort. We can have a look in the next slide, but in this slide, I want to show the chemical reaction. It is still a crystallization process, but the crystal of brucite is very fine. So you wouldn't be able to get a large enough crystal that you can separate directly from the solid phase. Therefore, this technology is limited to liquid phase recovery, but it can handle very high concentration of phosphate without the high concentration of ammonia. This could be very beneficial for example, aerobic digestion process, which will have very high concentration of phosphate, but no ammonia concentration, or very low concentration of ammonia. Or it could be applied to certain industrial process, including ethanol plants and even potato plants that produce a side stream that has very high concentration of phosphate and a low pH. So this is a unique process that could be beneficial for certain type of waste stream with very high concentration of very high concentration of phosphate and low pH. Next slide, please. This is one of the technology that is under development by Centricis and CMP, which is called Calprex. Essentially, it is a brushite reactor that take in the P-enriched centrate from acid phase digester and try to recover brushite from the process. In addition to that, this process can be modified to use as a carbon diversion technology that divert a certain portion of the highly concentrated volatile fatty acids into a mainstream biological nutrient removal process that is considered to be beneficial and economically friendly for biological nutrient removal. Next slide, please. Here shows the pilot plant we operated for a municipal treatment customer. This is a 10 gallon per minute process, include a full-size dewatering centrifuge, the reactor. The reactor is actually a laminar settler with modifications in the mixing process and also the sedimentation chamber. It has a fully automated control panel that can operate 24/7. And the recovered product is the dried brushite coming out of the trailer. This is considered a successful pilot study that is supported by the Water Research Foundation and tested in one municipal plant, but also received samples from multiple large and small treatment plants for the validation of the process. The take-home kind of message we learned from the effort is it is actually designed for recover very high concentration of phosphate from a low pH stream. So yeah, it's a very interesting process and can be very effective for the red condition. Next slide, please. As here you can see, the recovered product of brushite is quite different.